reminded ourselves about looking at electromagnetic phenomena in what's called macroscopic Maxwell's equations. That is to say, we're looking at electromagnetic phenomena when we're surrounded by media in the macroscopic world that's made up of a tremendous number of microscopic constituents, and we're not actually dealing with the details of all those. We have some macroscopic description, as you're familiar with in statistical physics, description of materials. So there are sort of some new players that you're familiar with. So we introduce, now we break, as we discussed last time, we break up the sources in terms of the so-called free sources. What that means is all of the charge that's not bound up together in neutral molecules and solids, atoms, etc. And the bound charges. And when we do that, what we found is that Maxwell's equations could be written in this way, with a modification of Gauss's law and Ampere's law, where we introduce the displacement field and the auxiliary magnetic field H. And they are related to E and B, the microscopic physical fields that are related to the forces through Lorentz force law, through combinations with the coarse-grained electric dipole density that we call the polarization, and the coarse-grained magnetic dipole density that we call the magnetization. So these are then form of Maxwell's equations after we've done that coarse grading. And as we discussed at the end of lecture, when the nature of the material is such that there isn't a macroscopic polarization or magnetization in the absence of an external field, then when we apply an external field, we will generally polarize and perhaps magnetize the sample, and the amount of polarization or magnetization will depend on the amplitude of the local field. And to lowest approximation, which is often an excellent approximation, that response is linear, meaning that the amount of induced polarization and magnetization are linearly proportional to the amplitude of the applied field. And that amount will generally depend on the frequency and spatial frequency, the temporal and spatial frequency of the applied field. So those proportionality relations in linear response theory are written in the Fourier domain. Also, generally speaking, the polarization that I induce in a certain direction won't necessarily be in the same direction that I push it in, because internal forces, say of a crystal, could make it that I push in this direction, but it polarizes in a slightly different direction. Which means that, generally speaking, the response function is a tensor. Okay? And when we write that in the domain, the time and space domain, then that is written back wrong. This is all just screwed up. Excuse me. Here's my eraser. So when I do the inverse Fourier transform, then we know that the Fourier transform of a product of functions is the convolution integral, where these are the inverse Fourier transforms of these. Let me emphasize that. I put a little filter underneath that. Okay? All right. So when we have linear response, then D and B are proportional to E and H. And those proportionality constants, again, are written truly in the Fourier domain. And the proportionality constants are the permittivity of the medium, which in general will be a tensor, and will generally depend on omega and k, and the permeability. Now, in many materials, most materials, if we're somewhat isotropic, then the k dependence is negligible. And quite often, if we have some kind of amorphous material, then the tensor nature is negligible also. And furthermore, depending on the nature of the material and the frequency, quite often the permeability is darn close to 1. Most materials, unless they're very special, aren't strongly magnetically responding. Typically the electric response. That's the most important. The permeativity is also when this becomes just some number, maybe as a function of frequency. We call it the dielectric constant. Okay. As you know, in SI units, the dielectric constant and the permittivity depend on the division by epsilon naught. The dielectric constant is dimensionless, but since we're working in CGS units, epsilon naught is 1. So the permittivity and the dielectric constant are the same thing. Okay? Okay, so if we restrict our attention to linear medium, and we'll simplify even further right now, where we're going to take the medium to be isotropic, homogeneous, and non-dispersive. This term non-dispersive, we'll explain what that means a little bit more in detail as we go on. But what it means mathematically is that we're neglecting the frequency dependence of the response function. These, as you remember, these functions we call the susceptibility. And when we have something that's non-dispersive, then the frequency dependence is negligible. What that means in the time domain, if you have something which is as a flat frequency response for some very large frequency range, then when you go to the time domain, when you inverse Fourier transform, that means that the time response is instantaneous. So that means that whatever the local B is at some space-time point, it's proportional to what E is at a space-time point. The same thing would be true for P. P would just be equal to, in the non-dispersive case, chi P. Perhaps it's a tensor, perhaps it's not. It doesn't matter. That's a non-dispersive, isotropic, amorphous response. Yes?
So, I don't know if there is one general range, but if there is, just ballpark, what sort of frequency do we generally, can we not make that approximation anymore?
That is going to depend very strongly on the nature of the material. Okay. And we're going to get into that maybe at the end of the lecture today, if not on Thursday. But the basic point is whether or not the medium has resonant response at the driving frequency. Okay. So, depending on the nature of the molecules or the solid whatnot, there are typically some natural resonance frequencies associated with the binding of the charges to the nuclei. And so far from any of the resonance, the response is fairly flat. But of course, near resonance, the response is very highly frequency. So the strongly dispersive response depends on the nature of the resonances of the binding of the charges within the material. Okay, so we're looking at a frequency band away from resonance. In some sense, it also means that it's not very absorbing either. They go hand in hand. And we'll talk about that in more detail probably next week. And there is a strong relationship between dispersion and absorption. And that has to do with that there's some physical response that's giving rise to both processes. And those relations are known as the Kramers-Krone's relations of linear response theory that we'll talk about a little bit later. Okay. I guess there's one last thing I wanted to say before I got to the linear. I forgot to write down in our review of last lecture, which is that generally what we have in terms of the energy in the field in media, what we showed at the end of last lecture was that the Poynting vector was given by E cross H. Moreover, if the medium is linear, then the energy density was E dot D minus, plus H dot D over A pi. Or if it's non-dispersive, isotropic, then this is often written as epsilon E squared plus mu H squared, using these relationships here. Okay? All right. So now what I want to talk about today is wave propagation in linear media. And what I mean by linear is what we just discussed over there. So let's begin by restricting our attention to the case of what we call dielectrics. So a dielectric is another name for a perfect insulator, or insulator. We'll talk about, right now we'll talk about perfect dielectrics, which means that there's no free charges or currents. Everything is bound up. Okay? So we set, in this case, going back over here, we can set the free charge and the free current to 0. So under that case, we have del dot E is equal to 0, del dot H is 0, del cross E is equal to minus mu over C, the H dt, and del cross H is epsilon over C dt. Okay, this is under the same conditions that we have in isotropic, homogeneous, non-dispersive medium. Okay? Of course, E and D and P and H are linearly related to one another. When I'm talking about wave propagation media, it's traditional to choose E and H as the relevant fields. they're all proportional in this case. And that's because, as we'll see, there's a nice relationship between, in thinking about the energy propagation in terms of E and H, as opposed to E and B. All right, so these are Maxwell's equations under the conditions that we discussed. And we want to now ask the questions about the wave propagation in such a medium. How do we get the wave equation, the relevant wave equations from Maxwell's equations?
Substitute.
What do we substitute what to what?
The curl equations.
Something like that.
The curl of that.
Take the curl of the curl. And then we'll do some substitutions. Okay, so we got to do that. So first, take your choice. Let's take the curl of this equation, the Faraday equation. So everyone should remember how you get the wave equation. You take the curl again. So the curl of E, everyone knows, is equal to the gradient of the divergence minus the Laplacian, is equal to then minus mu over C, the curl of that, and we can take derivatives in any order we like because we're physicists, and we'll ignore any kind of funky non-continuity issues that we might have to worry about. So now we do the substitution. Del dot E in this dielectric is 0, and del cross H is given over here. So we then find the minus the Laplacian of E is equal to minus mu times epsilon over C squared, the second derivative of the electric field with respect to time. Okay? Or del squared minus mu times epsilon over C squared d by dt squared times E is equal to 0. Okay? And similarly, if I had taken the curl of this equation of Ampere's law and done the same thing, I would find the same thing is true for H. Also, D and B satisfy the same wave equation. Okay, so this is the wave equation in 3D, just like we had before, but in a dielectric. That could be magnetic as well. So we know this. We can look for plane wave solutions. So both E and H there are plane wave solutions, and all we have to do then is determine the relationship of the parameters of the amplitude, wave vector, and frequency and direction, i.e. polarization, of those waves inside the dielectric. So the first thing we get when we plug this in here is we get what we call the dispersion relation, which is the relationship between omega as a function of k or k as a function of omega. How do we do that? Well, we just plug the complex representation into the wave equation. And so what happens when we plug that in is every del becomes an ik, and every d by dt becomes a minus I omega. So the wave equation then says ik times I dot into ik is minus the magnitude of k squared. And then I omega times minus I omega is minus omega squared over c squared mu times epsilon e twiddle h twiddle equals 0. And so, in order for this to be true, no matter what the amplitudes are, we have the relationship that k is equal to, the magnitude of k is omega over c times the square root of mu times epsilon. That's the dispersion relation. Okay. Now, of course, you remember that the phase velocity of the wave, let's say the velocity which with a plane of constant phase moves, as is given by, always, if we have this form, is given by omega over the magnitude of k. That's the phase velocity. And that is given by, according to this, c divided by the square root of mu times epsilon. So what we find from this, you remember, that the speed, the phase velocity inside the dielectric is not the speed of light in vacuum, but is changed by this amount. And that amount is called the index of refraction. So the ratio of the phase velocity to the speed of light in vacuum is the square root of mu times epsilon. And that's known as n, the index of refraction.
Should be 1 over?
Oh, sorry, c over that. That's the index of refraction. And under the approximations that we've made so far, that's a constant. It is non-dispersive locality flow. All right. What about the energy and intensity of the wave, of the plane wave in the dielectric? So the intensity, actually, before I do that, I guess it's important for us to think also about what is the relationship between the amplitudes of the fields and their relationship to the direction of propagation inside a medium which had no space charge, that is, say, no free charge. And of course, del dot H is always 0. Well, these are transverse waves, as before. Why is that? Well, del dot E equals 0 inside this medium with rho free being 0. And thus, what we have is ik dot U0 tilde is equal to 0, and that just means this is true. And similarly, the H field is perpendicular to the direction of propagation. So these are transverse waves. If we had so-called space charge, like in a plasma, this wouldn't be true. We can have a longitudinal wave. And what about the magnitude of H versus the magnitude of E? Well, we have, again, these fields are not independent of one another, but they're related to one another through the Ampere's law and Faraday law. So del cross E is equal to minus mu over c, the h dt implies ik cross into h naught tilde, oh no, e naught tilde, pardon me, is equal to I omega over c mu h naught tilde. Right? So this tells me that E naught tilde crossed into the direction of k is equal to omega over k mu over c h naught tilde. Okay, dividing by the magnitude of k, canceling out the I. So this is equal to, we just said, the phase velocity over c. Omega over k is the phase velocity times h naught tilde, which we said was equal to square root of mu epsilon, or the square root, therefore, of mu over epsilon. Okay? So if mu and epsilon are equal, then like they are in free space, then these guys are equal. But in general, they're not. And this constant, the square root of mu over epsilon, is known as the wave impedance. Yeah.
I think we need the k cross bit at the front of.
Yes, thank you. Sorry. The direction, that's the magnitude, but the direction is, as you said, thank you, k cross that is equal to that. K hat cross that. Okay? So the magnitude of E0 divided by the magnitude of H0 is the square root of mu over epsilon. Now this is one place, and I must, you have to give props where props are due. That SI units are much better. I know it's blasphemy, but the priests have to admit in their religion doesn't cover all. Now, in SI units, the magnitude of E naught over H naught is equal to the square root of kappa submagnetic mu naught over kappa of electric, where mu is kappa times mu naught, and epsilon is kappa times epsilon naught, right? Remember that from your undergraduate studies. We call this things dielectric constant. So this is the square root of kappa over epsilon, not kappa electric, times the square root of mu naught over epsilon naught. This is SI units. This thing has units. It's not a dimensionless quantity, it's got units. It actually has the units of resistance, because impedance is a resistance, right? And this is known as the impedance of free space. And does anyone know what that is?
Okay.
Did we hear that?
77 ohms or something?
Excellent. It's 377 ohms. It actually means something. You may have learned, maybe I hope you have learned, some point in your studies about so-called impedance matching. If you wanted to look at a wave propagating from one region to another, if the impedance is matched, then you get perfect transmission, otherwise you get reflection. So an impedance mismatch that causes a reflection of waves. We'll talk about that a little more. If I have a transmission line and I terminate it with a resistor of 377 ohms, I get no reflection. Yeah?
So you're saying that the impedance of free space is 377 ohms, right?
Yeah.
So if we have a less than that resistor, like a 1 ohm resistor, does that mean that the resistor has less impedance in free space, or does it impact that figure 78 ohms?
No, it has less.
Got it.
Yeah. So there is a natural impedance of free space. That doesn't appear anywhere. It's buried in the C's, the speeds of light. Okay, but one way to understand this relationship, the ratio of the amplitudes, is the electric field is something like volts per distance, or I'll call it potential per unit length, right? That's the units of electric field. In SI, that's volts per meter. In CGS, it's stat volts per centimeter, whatever that is. Whereas H is like current per distance. Well, of course, in CGS, it's got a 1 over the speed of light in there, but we'll ignore that for the moment. And so volts per current is resistance. Okay. Okay, but the bottom line here is really the following, is that in a medium, the amplitude of the electric field and the H field are not the same unless the ratio of mu to epsilon is 1. Okay, so I can impedance match the free space when mu and epsilon are equal. We can also think about that in terms of B. Remember, B is mu H. That means H is B over mu, and therefore this is equal to 1 over the square root, which is 1 over the index of refraction. If I were to write my electric field, if I wanted to know what is the magnitude of the B field in an electromagnetic wave in a dielectric. Okay. In vacuum, we said that E and B have the same magnitude, but inside a dielectric with index refraction n, they are not. All right. Okay, so now what about the flux of energy? So the Poynting vector, if we look at its time average expectation. Place. We look at its time average over a period. This is the intensity, if I look at its magnitude. And we know how to take the time average of a product of functions. This is the time average of E cross H. According to our lovely theorem, if both of these oscillate at the same frequency, then this is equal to 1/2 the real part of the complex amplitudes, with one of them star. That's the shorthand way of dealing with time averages when we have functions that oscillate at fixed frequency. In this case, this is E0 tilde e to the I kx. That's star crossed into H0 e to the I kx. So the intensity I is equal to C over 8 pi, the magnitude of E tilde 0 star cross into that. Which is equal to C over 8 pi, the magnitude E0. They're in the H0 because they're perpendicular to one another in the k-hat direction. Okay, so the propagation direction is the direction of flow of S, and the intensity is the amplitude of that, or the magnitude of that. The intensity thus is C over 8 pi E0 squared over the impedance. Okay? That's the intensity. Because E0 is related to H0 through the impedance. H0 is E over the impedance. Okay? What about the energy density? Well, if we wrote that down over there, that's going to be equal to, so the electric part of the energy density, let's look at the time averaged version of that. Averaged over time, that's the time averaged version of epsilon E squared over 8 pi, which is over 16 pi E0 tilde squared, using the trick that we just discussed. 1/2 the real part, and the real part is already real. E star E is E squared. The magnetic energy density, time average mu H squared over 8 pi is mu over 16 pi H0 squared. Which is equal to mu over 16 pi, the impedance squared, E naught squared. But the 1 over the impedance squared is, if we put in the impedance squared here, we get mu over epsilon. So this is equal to epsilon over 16 pi E naught squared. So what we learned is that in a linear medium, non-dispersive, the amount of energy stored in the electric field, time average, is the amounts stored in the electric field. They're equal to epsilon over 16 pi times the amplitude of the electric field squared. Just like in free space, the energy in the electric field and the magnetic field are equal. They're equal here as well, except scaled by the dielectric constant. So the total energy density is the sum of this is epsilon over 8 pi E naught squared. So if we look at the time average Poynting vector, which we said was equal to C over 8 pi times E naught squared over z in the direction of propagation. And we plug in z is equal to the square root of mu over epsilon. And we multiply top and bottom by epsilon. Then what we see here is that this is equal to c over the square root of mu times epsilon e squared over 8 pi in the direction of propagation. This thus tells us that for a plane wave in a linear dielectric, the flux of energy is equal to the phase velocity times the total energy density propagating in the direction of k. So for a plane wave in a linear dielectric, this is the relationship between the Poynting vector time average and the energy density. The flow of energy is at the phase velocity for a plane wave. Okay? Any questions so far? All right. Some of this, I'm sure, is review. A good chunk of it, but it's good to see it. All right, I want to slightly generalize now to the case where we allow, so now let's talk about what I would call a general non-dispersive linear medium. With finite conductivity. Okay? So I'm going to allow the material to conduct a little bit of free charge. What that means is that we have an additional kind of constitutive relation that's analogous to these relations, which says if I have an applied electric field, then I'm going to get a current, according to Ohm's law. So you remember that Ohm's law that we talked about some number of lectures ago can be written as a relationship between the current density and the local electric field. Now, generally, that relationship, like everything else in our discussion, well, I guess only is exact, that proportionality in the Fourier domain because of finite response. In fact, in your homework, problem 3, you're looking at the case where we're looking explicitly at the frequency dependent in problem 3 of the conductivity. Again, generally the conductivity is a tensor. You apply a voltage in one direction, you don't necessarily get current flow in that direction, depending on the internal structure of the material. Okay, but in the simplest case, for amorphous, or for, well, I'll just say, for a homogeneous scalar non-dispersive response, then we would say we would again just have a local relationship with some constant we call the conductivity. All right. So now, what about the charge density? Well, whatever, this is my free current density that's now flowing, that's unbound, as in a solid that has some finite conduction band. But we know from conservation of charge that, however, that the change in the free charge depends on minus the divergence of the divergence of the free current density. And when we have a linear response in this manner, then we have this is equal to minus the conductivity dotted into the divergence of E, whatever the local electric field is. But del dot E is related to the local free charge density according to Gauss's law. So we can plug that back in. So that is minus 4 pi sigma over the dielectric constant times rho. So what we have then is a simple differential equation which says that inside this conductor, the free space charge decays, assuming these are all positive numbers, exponentially. With a time scale that depends on sigma over epsilon. Yes?
In a second,
Oh.
just the function of x.
I'm sorry, I meant to say this is time 0. Excuse me?
No.
Sorry. Yeah. So what this tells us is that if I have a reasonably good conductor, after a time that is inversely proportional to the conductivity, and conductivity has units of a rate in CGS. It's related, as you remember when we talked about the Drude model, to the rate of collisions that give rise to the finite conductivity in a real solid, or whatever the material is. So after time t much, much bigger than 4 pi sigma over epsilon, rho free equals 0 inside the conductor. That doesn't mean that conductivity, I'm sorry, doesn't mean that the conduction current goes to 0. It just says that whatever it's flowing, it's not building up any local free charge density. Whatever charge density there is can be at the surfaces. This doesn't say anything about the discontinuities. There's all kinds of funkiness that we swept under the rug in terms of the surface effects. Because, of course, if there's surface effects, these derivatives have discontinuities and things that we're ignoring at the moment. But inside the bulk of the conductor, the current density goes to 0 exponentially fast. So, with that said, if we make the assumption we have the Maxwell's equations after this time scale inside the conductor, and that time scale can be very short. So that now we have, including this assumption, we still have del dot E is 0. We have del dot H is 0. We have del cross E is minus mu over C H dt. But now we have conduction current, which was J free, is sigma plus epsilon over C dt. So what we have modified now is the addition of a term that came from the free current density, which according to Ohm's law is sigma E. All right? That's the addition to Maxwell equations. Okie dokie. So now I want to know, how do waves propagate in this kind of medium, which has a finite conductivity? How do I find the wave equation?
Substitute.
No!
Take control.
Yay! Yes, take the curl. All right, let's take the curl. So curl of the curl of E is equal to the divergence, the gradient of the divergence minus the Laplacian is equal to minus mu over C d by dt, the curl of H. And since we made the assumption that the free charge went to 0 pretty quickly inside the conductor, the free charge density, I should say, not the charge itself, the local density is 0, then we can plug in over here. We get minus the Laplacian of E is equal to minus 4 pi mu sigma over C squared d by dt of E minus mu epsilon over C squared d squared by dt squared of E. Check that my sign is right. Looks good. Okay. So we have a modified version of the wave equation now. Something perhaps you're not as familiar with. It has this first derivative term in it. So we have del squared plus 4 pi mu sigma over C squared, minus d by dt minus mu epsilon over C squared d by dt squared acting on the electric field. And similarly, it would be the same thing for the H field. 0. Okay. Once again, there are plane wave solutions to this, is the modified wave equation, which includes the finite conductivity. Once again, we can take the solution that's written over here and plug it in to this equation. So let's do it. Just like we have over here, we take these ansatz, anzai, what's the plural, ansatzes, and ansam, and plug them in. So every del becomes an ik, every d by dt becomes a minus I omega. And we get minus k squared. So I'm going to plug in plane wave ansatz. And I get minus k dot k plus I 4 pi mu sigma omega over c squared minus mu epsilon omega squared over c squared plus u, either E0 or H0 to 0. So, we have something new and interesting. What we see in this case is that in order to satisfy, for this ansatz to be a solution to the wave equation, the only way that's possible is if this wave vector is a complex number. Or let's say it's a vector with complex coefficients. Particularly the magnitude of k, solving for this, is the square root of mu epsilon makes her to c squared plus I 4 pi mu c squared, which I can write as 1 plus 4 pi sigma so we have a very different kind of dispersion relation inside the conductor. Our wave number, as written here, is a complex wave number. It has a real and imaginary part. What does that physically mean? Well, let's take a look. The physical field is the real part of this complex thingamaboozy, the technical word. So let's look at the particular case. Let's just simplify life a little. Let's not talk about complex polarization and all of that. Let's just say, let's say I have a wave, linearly polarized wave propagating in the z direction. So let's look at E, its function of z and t, is the real part, so real vector E0, e to the I k tilde z minus omega t. Okay, so now k tilde is a complex number, which means it has a real part and an imaginary part. Let's just write that as k sub real plus I k sub. So this is the real part of that number, and this is the imaginary part of that number. So e to the I k tilde z is e to the I, the real part, and then I times I is minus 1. Okay? So, I plug that into here, and what I find is that, assuming this is a real vector, because it's linearly polarized, and I'll just take its phase to be 0. Maybe I'll make it around twice. Here, wrong record. Right big, right big. Plug that in, and I get E0 cos the real part of the wave number, and then e to the minus the imaginary part. So, what we learn from this is that when the wave number has an imaginary part, it has to do with some kind of, if this imaginary part is positive, then this has to do with attenuation. That's to say, a decrease, an exponential decrease of the amplitude of the wave coming from this finite conductivity. Work is being done on these charges and being absorbed. And therefore, the energy, as we see, because the amplitude is decaying, the energy is decaying and it's going into heat in this particular case. There are other ways you can attenuate a wave. You can attenuate a wave by scattering, right? I mean, I send a wave through a material that disperses the light into other directions. That will also attenuate the propagation of the wave as well. But that's all accounted for whatever gives rise to this imaginary part. Of course, if for some weird reason this were negative, well then this would mean that the amplitude of wave was exponentially increasing, and that is amplification. So if somehow the material dumped energy into the wave and increased its energy, we would amplify it. Yeah?
Would a laser be an example of that?
Exactly, indeed it would be. A laser, a maser, radio frequency amplifiers, etc. Okie dokie. So what we also see from this is that the phase velocity depends on the real part, because the velocity with which the phase moves depends on the real part of the wave vector. Okay? And so the index of refraction here has a real part. It also has an imaginary part, which has to do with the attenuation. Let's take a look at what the real and imaginary parts are for this particular case, where we're looking at a medium that has, in which we put in a finite conductivity. So for the case at hand, well, how do you take the real and imaginary part of this complex number?
And if it was small enough, you could just.
Indeed. So we will look at some limits of this, which are interesting. But I want to ask you, how do you take the real and imaginary part of a complex number?
Take complex number, add them up.
Right, so we'll get something about the magnitude if we did that. And then I gotta take the square root of that.
You can take the sum of the itself and use context conjugate.
Okay, I could do that, but I still have the square root in there. To take an exponent of a complex number, you write it in terms of amplitude and phase. Always. Okay? So if I have a complex number z, and I want to know what it is to some power, whatever, name a letter, p. I write this as the magnitude p e to the I p phi. And then if I want to then find the real and imaginary parts of this is the cosine of p phi plus I, the magnitude of z, sine of p phi. That's how you take the power of a complex number. All right? So we could do that here. I'd have to write the amplitude and phase, as we said, multiply by the complex conjugate, get the amplitude, the phase is related to our tangent, and we would get that. But I like Jacob's suggestion, let's look at this in some limits, because then we'll get a little bit more insight about it, we'll just get very messy expressions. Okay, everyone remember this? High school? All right. I know, it's easy to forget, because we never use it. Not so often, at least. All right, so let's look at the case where we have a poor conductor. So what does that mean for this conductor to be poor? It means that that imaginary part is small. And what does that mean? What does it mean to be small? It means that the ratio of omega to the frequency at which I'm applying, and if there's a finite dielectric constant, epsilon, is much, much less than 1. This is a dimensionless number. Okay? Sigma has units of a rate in this units. So then, in that case, I can just use the binomial expansion here. And write this as 1 plus 2 pi sigma over epsilon times omega. Approximately equal to. Okay? So the real part here is just as before. And the imaginary part now is equal to 2 pi square root mu over epsilon. Did I do that right? I think I did. Yeah. Sigma over c. All right. So what does the wave propagation look like? Now I realize there's one little factoid I forgot to remind you of before we get to that. Let me do a little aside. If I am looking at wave propagation inside a medium, we said what is the wavelength inside the medium?
Shouldn't there not be an I on the second exponential?
Yes, thank you. Well, the wavelength depends on the period inside the medium. It's 2 pi over the real part of this, which is equal to the phase velocity over omega what am I saying? Yeah, k is equal to omega over the phase velocity, right? So that was right. Phase velocity over omega to pi, which is d phase over nu, which is c over nu times 1 over the index of diffraction, the real part. So the wavelength inside the medium is related to the wavelength in vacuum by the index of refraction. Now this, one point here that to emphasize here is that the wavelength changes, but the frequency doesn't. Okay, if I have blue light and I don't have any kind of frequency conversion, I have linear response, it's blue inside the medium too. So why is it that the wavelength changes, but the frequency doesn't? Yeah?
Does that have to do with energy conservation?
Well, that's an interesting point. I guess you could think about that from the point of view in quantum mechanics, of course, the frequency and energy are related. It's a classical phenomenon too. And of course, the frequency, it's not the frequency that determines the wave, it's the amplitude of the wave. I mean, they're interrelated. That energy conservation is related through the notion of the response of the medium. But if the response of the medium is linear response, then when I drive the system at a certain frequency, it responds at that frequency. So if I have a wave, let's look at it as a snapshot in time. Here it is, coming into the medium. Well then, what I claim is assuming, let's say, the index of refraction is positive, then the wavelength is shorter. So what's going on? Well, if I'm sitting here in vacuum, and here I'm inside the dielectric, I will see the peaks come up and down to me as this wave travels at the speed of light. Now I'm going inside the medium. The peaks have to go up and down at the same rate because it's a linear response. But if they're going to come up down at the same length and the speed is less, well then the wavelength has to be shorter so that I see the peak go up and down at exactly the same period. So if I'm an atom or an antenna, I will see the same frequency of oscillation, but the spatial distribution of that wave is different inside the medium than in vacuum. So the wavelength is shorter, but it's the same color. All right? Now let's add in the conductivity. What does that mean? Well, what that says is that if I have, this is a horrible picture, the amplitude is going to be the same, I don't know if you can kind of see that. If I'm in a conductor, well then, this, assuming this will attenuate. So there is a depth of propagation into this medium depending on how big K sub I is. If I have a very good conductor, let's just conclude with that. then my conductivity is so big compared to these ratios that I can ignore the real part there, and my K tilde is approximately equal to I have 4 pi sigma over 1/2 power, which is the square root of 4 pi omega sigma. Over C, I to the power 1/2. What is I to the power 1/2? Thank you. Which is square root of 1 over square root of 2 plus I 1 over square root of 2. Okay? So the real and imaginary parts are equal in this case. And the propagation distance is tiny then compared to the free space wavelength. So I will get almost no propagation into the conductor. It almost, in fact, that decay amplitude gets very rapid as sigma gets very big. And for a perfect conductor, I have 0 propagation into the conductor. I have perfect reflection. And the depth that goes into has a little skin deep penetration is known as the skin depth, which is equal to 1 over the decay amplitude, or the decay rate. Actually, it's in terms of the energy, so it's given by this. As k sub I, the imaginary part of the wave number, gets bigger and bigger and bigger, the rate of exponential decay gets bigger and bigger and bigger, which is to say the depth into which it propagates goes to 0. And when the skin depth is tiny, then there's very little propagation, there's very little dissipation of the wave, and you get perfect reflection. So if I had silver, a silver mirror at optical frequencies, I will see it's basically a perfect reflector. If I had X-rays, as we'll see, it's almost transparent. I'll just go right through it. I want my X-ray glasses. All right.